Right, so on the bench in front of me today, it's I finally cleared a lot of stuff that needed fixing out of the way. I still have a guitar amp here with an intermittent fault, which is going to be fun. Oddly enough, it's actually my old shift manager's son's amp, but anyway, that's a different story. So yeah, I've got here a broadband audio transformer, so it's designed to work from 20 Hertz to 20,000 Hertz perfectly with no losses whatsoever. That's just impossible, but yeah, that would be a perfect transformer. Signal generator, sine wave, square wave. I've obviously got it on sine wave because I'm doing audio testing. That there is a buffer circuit, just a couple of parallel op amps to drive a transformer, and that there isn't some dodgy wire shoved in an IEC lead and a transformer running it. Just imagine that is a full European class 2 rated, fantastically built power supply, and not something I knocked up in 5 minutes with some bits I had lying around. So the transformer down here, when it comes to transformers, they can be quite tricky to measure, because if you put an inductance meter across the primary, it will just give you nonsense. You can use an inductance, if you short the secondary, you can put an inductance meter across the primary and it will give you the leakage inductance. It's quite handy for that, but to actually find the proper inductance, it will give you nonsense. So what you do, you get a sine wave. I'm not sure how well that's coming out. It's saying it's slightly overexposed here, but I shall see in the edit. You then feed that into a capacitor of a known value. That then sits in the primary of your transformer you want to measure. Transformer goes back. You then measure, we put the oscilloscope at this point and at this point. And so what happens is, as the frequency is varied, at some point these two will end up creating a resonant circuit. The frequency will match the resonant circuit and there will be a peak in the voltage. Just like anything at resonance, like a plank of wood, a long plank of wood, you know, you can start wobbling it up and down, and if you get the speed you're wobbling it right with very little energy, you can get the thing to really start wobbling quite frantically. So have the oscilloscope over here, and where are we? There we are. So what's showing on the screen here, that's the input, that is the actual across the transformer. So this is what's coming out the signal generator, and this is what's going into transformer. So you see at this frequency, if I put the differential trace on as well, very little of anything going on there. The two traces match. They are both at pretty much the same RMS input going into them, and the phase between the two of them, there's very minimal phase discrepancy. If I actually up the frequency, that's the amplitude, don't want to do that one. If I up the frequency, you can see it remains fairly constant. However, if I keep dropping down in frequency, you can see just around there, somewhere around the 1.5 kilohertz, the purple line, which is, so that one is channel 1 minus channel 2. You see it starts rising up, and here's the interesting thing. So the yellow is what's coming out of my driver circuit. You can see as I vary this around this point, it remains fairly constant. Some of these readings are more going to be down to the fact I'm changing wildly in frequency compared to the time base of the scope. So its sampling rate per each division, basically the amount of sine it samples, changes. So obviously there will be some natural drift on the oscillator output as well, but as you can see, the voltage across the actual primary of the transformer starts rising considerably, and that is because it is reaching a resonant peak. So I just need to find the frequency at which that peaks out, which is somewhere around there. So what have we got? 1.42, 1.4, 1.42, 1.4. It is about there. Can I just go up a touch in the voltage? 0.46. So yeah, I'm about there somewhere. So interestingly enough, look, it's it doesn't seem to want to be able to measure the frequency of it now. Let's change the time base. There we go. So 1.48 volts at about 363 hertz. Can we get it any higher? So no, it is right on there, about 300 and let's call that 360 hertz. So let's go down and do some maths. So the maths to work out the frequency, not the frequency, the inductance is going to be 2 pi capacitance squared times by the frequency. I believe it's 2 pi because it's your standard angular velocity. It's a sinusoid, so it's obviously got 360 degrees in total. There are 2 pi radians in the circumference of the circle, so that's why it's a 2 pi formula. You find that a lot. It's got me when I first started doing electronics. You start getting into frequencies and stuff. I'm thinking, why does pi keep cropping up? And obviously I had to then go and learn why that's all about on there. So let's do it that way. It'll probably just be easier. Let's see. 1 over 2 pi is about 6.28 times by, no, I've done that the wrong way around, that's not right. It's frequency, and that's going to be capacitance. 6.28 times by 300 and let's call that 355. Let's take the 1 off there. We'll do that next because it just makes life easier. 2,229, so 2,229 times 2 equals 4,458. C is going to be 1 times 10 to the minus 7, so like 102 times 10 to the minus 9, which is going to be 0. Oh, I seem to have lost my mate, telling you, whenever you try and do anything when you're talking to a camera, you just mess up constantly. It's just like the law. 6.28 times by 355, I said, didn't I? 2229, 2229 times 2229, and times that by 0.00000012345 102. That's what my capacitor measured, about 102 nanofarad. 0.506, 1 over 0.506, about 1.97 henries. 1.97. So 1.97 henries. Yeah, that's not bad. That's not bad at all. Interesting. So inductors, it gets me. You go on any electronics forum. So if you put 2 inductors in series, they're basically the same as 2 resistors in series. You will just get the value will become L1 plus L2, and if you have a third one in there, plus L3, and so on and so on. So you basically get, if each one of these was 1 Henry, you would end up with 3 Henries of inductance. If you put them in parallel, you get your standard product over sum, so you will get L1 L2 over L1 plus L2. And if you have more of them, where you can either work them out individually like that and turn that and make that L1, then make L3 L2, or it's like resistors, which is 1 over now I'm thinking what is that? Yeah, it just went blank for a second. And yeah, it's 1 over, and then it's going to be 1 over L1 plus 1 over L2 plus 1 over L3, and so on and so on. Same as basically what you're doing with resistors. However, if you put two inductors in series on the same core, something happens. So let's say that's your core, and so you've got your coil of wire going around it, and so that's your inductance. If you then take another coil of wire, let's say it's equal length, instead of connecting here, you're now connecting here. Although you've essentially put two inductors in series, unlike when they're just two separate ones, you've now put them on the same core, so all the lines of force from every single one of these is cutting through all the other ones. Now, if you go on any forum, people say to you, if they're on the same core, it's 4 times the inductance. That is just not true. I can show you on here in a bit. The formula, I had to look this one up because I can't say it's one I use a great deal. LT, which is going to be the total inductance, is actually equal to L1 L2 minus M2, M squared, yeah, let's do it up there, and that is over L1 plus L2 minus 2M. And so you've got a product over sum equation here, however obviously this bit has to come into it, but M is essentially the coupling ratio of the core between these values, and it's an unknown. It's one of those ones you'd have to measure like this first to figure out how much your inductance increased to actually then resolve what M is. So I've now taken one of the windings out of circuit. So the primary now is just running half of the primary essentially. It's two primaries wound on the same core, but I'm now only connected to one of them. So let's just tweak some settings here, get that to about a volt. Right, so currently at about 8 kilohertz, dropping. And you see already it's clearly peaking at a much higher frequency. Somewhere there. About there, see 1.3. So about there, wrong way. About there is the peak. 2.8. So about there. So going back to the equation I used earlier, so that's now at 1.025, so 1025 hertz. So 6.28 times 1025, 6437 squared times my 102, 4.22, 1 over 4.22 becomes a mere 237 millihenries. And so if the constantly peddled idea that two inductors on the same core in series quadruples in value, then if they're 1.97 henries in series, then one of them should only be, or should be about 0.49 henries, but it's 0.237, so the total value, the total difference is 1.97 over let's say 237, 8.3 times. So putting the two in series on the same core increases the inductance by 8.3 times. And so if you give me a minute, I'll work out what the M value on this must be. So crunching a bit of maths, and I get a value of M, which is the mutual coupling between the two inductors of 155 millihenries, which would, if you put it into there, so product over sum, taking into account the 155 millihenries of mutual coupling between the two inductors, 237 millihenries becomes 1.97 henries. Whereas if you was to just try and do the product over sum equation of saying that they were two inductors, if you was just to do the series equation, saying there was two inductors in series, which is what they are, you would only get 474 millihenries. So as you can see, big difference. So yeah, that is just something, I guess, to take note of. I'm rambling on and on, as I have a tendency to do that. Yeah, and what is that? It's like, I don't know, that clock's a bit slow. Where are we? Can I focus on that? Yeah, it's like, I don't know. Do you know, I've got a phone in front of me. Yeah, 12:30. Yeah, it's 12:30. So yeah, so that's that one sorted. So the next thing to do is to try and ascertain at what point this thing wants to start distorting. Now, this frequency oscillator isn't the best in the world, so yeah, here we go. Now we're back to that. So remove the capacitor from the circuit. As you can see now, there's no more peaking. The purple line is constant, so we can just remove that. So I need to start dropping in frequency and seeing. So those op amps are happily driving that down at 40 Hertz. That is actually my oscillator, I think, more than anything else. I can soon find out if I remove the transformer. So yeah, not a great deal of difference. That's more the oscillator itself actually throwing a pissy fit than the transformer. You know, and there is a bit there. Look, 17 Hertz. You can see I'm starting to overload the op amps at that point. That's more than reasonable. Realistically, there's not a lot in music that even goes down to that level. So you just make sure you put a filter circuit in, like a 24 decibel per octave slope on a filter circuit, which cuts it off. So that's that end of things. So what I might as well do is put the second channel to use on the primary. Come around here, and see. I'll change the scale. I've managed to invert that. Let's swap them leads around just to stop confusion there. So I can actually see how much of that is coupling through from the secondary to the primary. That's better. So and Christ, what's that? 17 Hertz. So there's some distortion there. But after that, and bear in mind this isn't like the best transformer in the world. I've really got to stop knocking that camera. Get you a better view on that, I suppose. So yeah, lower frequencies. Let's come down. You see, some of that is my oscillator, but there is a slight distortion around the low 20 Hertz mark. And you know, that's near inaudible anyway. Most things, most speakers, and especially in most domestic setups, most of them sort of sub 50 Hertz is completely missing. Yeah. And as you can see, the interesting thing is there's no drop off. You know, it's coupling through to the secondary. As we go up in frequency, and there's no phase shift there between the primary and the secondary. That is nice. 14 kilohertz. Well, look, we're way past the point of hearing there. 24 kilohertz. More than acceptable. So, yeah, that's basically just. So it's for my next project. It's like I say, it's going to be a DI box. So the next test I have to do is this transformer clearly says on it, do not, on the data sheet, do not pass DC through the windings. However, That's probably more likely, as in it's to stop you from trying to use this thing as a single-ended transformer. So like, as in, if we go back to the paper down here, as in wiring it up so that you had your transformer, let's actually draw some windings, shall we? So you had your transformer like that, and let's say, I don't know, let's just put, we've got a valve in here for some reason. It's to stop you from having that going to the plus voltage and trying to modulate the current single end, because all that happen, it'll push, if you get the BH curve, you're just going to push it up to here somewhere, and the core is going to be in saturation, whereas it needs to be here. So if, however, you pass current in opposing directions through both primaries simultaneously, the two counteract and you don't end up with that problem. And when I'm talking like a couple of milliamps, and if I get my meter out and measure the primaries, I should very much say the DC resistance of them is going to be quite low. Yeah, you wouldn't want to be trying to pass like an amp of current through the things, because that would just be stupid. However, a couple of milliamps really, as long as it's very well balanced, and likewise, you know, if I do go down that route, not only will I just be balancing the current, I will actually be doing extensive AC testing to make sure that it truly is balanced and behaving as it wants to, as it should do. Let's see. I think I've killed one of these probes. Right. That is the primary. So when you're talking 20 ohms, so you can see a slight difference there. So, you know, small current. That would help even more. Oh, behave. Come on. Behave for me. Oh man, seriously. Yeah, one of these probes is foobarred. So we're talking 10 ohms. So if you was to pass an amp through a 10 ohm DC resistance, you get 10 watts. If you pass 100 milliamps through it, you get 1 watt. If you pass 10 milliamps through it, you get 100 milliwatts. And if you pass a milliamp through it, you get, I completely forgot where I was there. It's late at night or early in the morning, again, perspective and all that. 1 times 0.1 times by 10. Yeah, you get something, microwatts. I think. Oh Christ, man, seriously, math shouldn't be that hard, but this time of the morning and nothing's making sense. 1 amp's 10 watts, 100 milliamps is 1 watt, and 10 milliamps is 100 milliwatts, so 1 milliamp should be 10 milliwatts, I think. It could even be less, because of course it's a square, isn't it? It's current squared times resistance. So of course, yeah, as current drops, the voltage across it drops as well. So yeah, it's even lower than that. It is yeah, it is multiple zeros. So yeah, it is 1 times 0.001 times current squared times resistance, 10. See, milliwatt. It's 10 microwatts, so you know, 10 milliamps through that transformer. I am talking quite a lot now. 10 milliamps through that transformer, power dissipation wise, you essentially will get the sum of the two. So 1 times 0.01 times by 10 times by 2. So it would be 2 milliwatts of power. That will happily dissipate a couple of milliwatts of power all day long. So yeah, it's like I say, it's going to be more of a BH offset curve thing than it is an actual power dissipation thing. So yes, next part of this video, and I might trim this one down a bit, probably should do, is going to be me testing that actually passing DC through the windings, even so it says not to. So yeah, anyway, I don't know how long this video is going to have ended up. Likewise, you know, you take various parts of it and try and cut them down a bit. But again, if you have still been watching this, as always, thanks, and catch you on the next part.